Hello, everyone. Let's tackle another system design. Um, okay. So, um, okay, we want to talk about uh, Amazon store or any online shopping platforms. So, this is one of those online system designs that we need to handle. So we will see how we want to go for the architecture. But if you remember, we have three type of system designs: online, batch, and stream processing. This one is the online one because users need kind of immediate or fast response when they do the shopping. It does have some async aspect to it as well, like shipping, payment. However, the first part of it, interaction of buyers with this online platform, is an online system. So let's dig into the functional requirements. Um, we should ask few questions, but at the end, we come up with some functional requirements like users can view a list of products, user can see each product detail, user can add product to their shopping cart, user can check out and pay, and then user receive notification after they finish shopping, and maybe after the shipping is done, user can comment and rate a product. Non-functional requirement are system need to support high scalability. User base is at the global scale. Users are all around the world. So this is highly scalable. Number two is that high availability. We want 4.9 availability, which means only an hour downtime. High consistency is needed for product availability and payments and orders. So when there is an order, we need to make sure that we adjust product availability count, and also payment needs to be done correctly at the same time. If any piece fails, it means that we need to roll back. So high consistency for this part. And then concurrency should be handled correctly, especially when there is a high concurrent environment. Let's say maybe at Black Friday time, there are many concurrent users and transactions, and we need to make sure that let's say we don't sell the same product to two people. It needs to be handled. Concurrencies matters in this type of systems. And at the end, low latency. Let's come up with some number. Less than 200 millisecond is a good number for low latency. We don't want to for our users to keep waiting, which is a not desirable user experience and will cost our revenue. We will lose revenue, which is the most important aspect of this type of systems online shopping. So let's talk about the scale. Daily active users, 300 million products, 100 million items. Throughput, each user buy one item per day on average. Then it means that 300 million purchase per day. Then if we divide this number of transactions by number of seconds in a day, 10 to the power of 5, it means 3,000 transactions per second. However, at peak time, like Black Friday, it can be 10 times. So let's At peak, we might have 30K per second transactions. So obviously one server cannot handle this and we need distributed systems. Assume one purchase takes 200 milliseconds. Okay, this part of the calculation is when they ask for, okay, give us some idea of how many servers do we need. This is some extra steps. You might not want to do all these calculations, but I'm bringing up here so that you can know how you want to tackle this. Assume one purchase takes, as we aim for, like 200 milliseconds. And then in 1 millisecond, there are, if you divide 1 millisecond, 1 second to 200 millisecond, it means 5 transactions if we have one thread. One thread, however, one commodity server has 250 threads, so it means 1,250 transactions one server can handle per second. If that works at 100% of capacity, but normally, I mean, that shouldn't happen. We should not expect overload servers. So let's assume 40% of our servers work at 40% of capacity. Then it means 500 transactions per second. 30K divided by 500, it means 60 servers. And this is with no replication, but for fault tolerance and also for availability, we always have like 3 replicas. Then we will end up to have 180 servers, distributed servers, to handle this scale of transactions. Let's say shard key, whenever now we know that how many servers do we need, but how we want to shard our app servers, how we want to route, like requests to different servers. Let's say we might go with user ID or transaction ID. However, user ID can cause hotspot here. So that's why, I mean, let's say one user is so active and they're making many transactions, then that might cause hotspot. So we prefer transaction ID. Okay, let's talk about storage. We said we have 100 million products. If each product size is 500 kilobytes, then it means terabytes of data for storing products. However, the bottleneck is not product, it's transactions, because it's ever growing. Transactions, we said we will have 300 million purchase per day. If each transaction has size is 200 byte, let's do quick calculation. One transaction consists of ID, user ID, timestamp, product ID, count, other info, and price. Let's assume this is like 200 byte, and then you just multiply 300 million transaction in the size of each transaction. And then how about this is for one day? How about a year? Then you multiply on 365 days per year, and then 10 years. It'll be like 24 petabyte, which is a huge number, and definitely it doesn't fit into one database server. Then that needs to be scaled. Okay, one commodities database can handle 10 terabyte of data, and then if you divide these numbers, you come up with 24K servers, again without replicas. We need at least 3 replicas for availability. So data model for this type of system, online shopping. is user, ID, name, email, password, address, phone, payment info. Product, ID, name, availability, purchase count, and description, image URL, and unit price. Shopping cart, ID, user ID, then a list of product ID, unit price. Order, which is ID, user ID, timestamp, total price. Status, which is like confirmed, rejected, pending, shipped, order, received order, returned order, and order detail, which is ID, order ID, product ID, unique price. Let's talk about API design. API design, we will have first, as we said, we want to see the list of products. So we will have a get API, which is /v1/products. Then like which returns list of product. Get v1 slash product slash ID to get the detail of a product. Post v1 checkout. This is a post. When they do checkout, it means they place order, and this is a post. Parameters, user ID, shopping cart, timestamp. And here is the high level design. So we go with microservices. So we have a user, load balancer, and then we have a couple of different microservices. First of all, we have a user service, which we store user information. And then the load balancer is super important. Whenever here is like user is going to there are many users can reach out to our system, so there is always a load balancer needed in especially online system design, which does rate limiting, security, caching, and it provides a layer of security and system discovery for all our microservices. So then we have a product service which store product information in a product store. This can be a NoSQL DB, and then product images can be on a cloud. And since like product is kind of static information, is not updated very frequently, especially like the most popular products can be, like calculated by an analytics ML service in some intervals, and then we feed that data in product cache to have a fast user experience, especially when they first load the first page when they list the most popular products. And then we have order service. For product service, we will need another product availability database, which has the number of products available, and then this needs to be in a kind of transactional database. If we want to go and combine the two, then that is better to be a transactional database, not NoSQL DB. But we can decide to combine product availability with order database, because they have some transaction aspect to it. When an order is placed, product availability, it needs to be updated. So if we want to avoid distributed transactions, we'd better to combine these two databases into one. However, that is kind of a little against microservice, like definition, which means each microservice should have their own databases. If we are very obsessed with microservice paradigm and the concept of the definition of microservice, then we might want it to be separate database. Then we'll have to some sort of distributed transaction. Then we have order service. does have order database, which is another transactional database. And after order is being placed, then it's time for the user buyer to make payment. This is a little interesting because it might take a while for the payment to be done. Maybe there are like some risk analysis and all that credit analysis, verification, all that. It might take time, and we don't want to make it a sync process. So order service wait for payment service to complete the transaction. So we can go with some kind of fire and forget um, uh, communication here. Order service place the order, and then it's done. But introduce a webhook so that when payment is done, payment service can call back the webhook, and then kind of a callback API, so that now order service knows how to update order database and product availability based on whether the payment is rejected or accepted. So there's like a little detail here. If payment service calls order service webhook callback very often, then it might overload that. So then we might need to use like a queue here, so that webhook does put payment result in a queue, and that's all webhook does. And then order service reads, let's say, rollback or committed queues, and then update order status, whether it is rejected or accept, completed, or what. The same kind of async, communication exists between order service and notification service as shipping and shipping service. We are using message queues because there's no need for these communication to be a sync communication, and it can be definitely be like an async paradigm, so that once an order is placed, now notification service can send email, let's maybe text messages to the buyer, and then also shipping service can handle the shipping part, and then update back the order service by another message queues, resolve message queues, so that again the status of orders change to, for example, shipped successfully, something. And yeah, that's it. And about deep dive, I think I covered most of this already. The most important point here is transaction requirement. To place an order, there needs to be a distributed transaction to decrease product availability. Place an order, also called payment service. If either of these steps fail, we need to roll back all changes. We could choose to have order and product availability in one database. I already talked about it. Because one database, transactional DB does have ACID properties. So, handling transactions, it's way more efficient and simpler with the transactional DBs. But again, this is a trade-off. If not, then we need to use Saga pattern. If we don't go with webhook, then we need to use async method, which is called Saga method, which is different from. This is a method for distributed transactions and different from two-phase commit, two-phase commit does need a coordinator, which calls different microservices, and then also send commands for rollbacks or commit transaction to each microservices. But there are some drawback for this method. First of all, the most important one is that the coordinator service is a single point of failure. So that's why we prefer Saga pattern, which is an industry standard, and Saga pattern is the same method that we already discussed, using some message queue in between services, so that to make them decoupled, um, and to implement distributed transaction. One microservice does its part, and then another microservice reads messages, does its part. If this, let's say, shipping, not exactly the shipping, but if, let's say, payment is more important. A payment fails, then it will go back with like a rollback message in a queue, so that order service can roll back order status and product availability to the original amount. So this is called Saga pattern in like a very brief explanation. But if you are interested, you can look it up and learn more about it. And then, yeah, order service called notification service, and I already talked about this. And the good thing about this async design is that different services can be scaled independently. For low latency, we need to store a list of most popular. As we talked, we want latency to be less than 200 milliseconds. So we need to accomplish that. We need to store a list of most popular products in a cache, so that it can be fetched and shown in the first page fast. This can be calculated and populated in cache offline using an ML model. I already talked about it. We can auto scale all app servers, because these app servers, like product, order, payment, these are all stateless um, servers, and they can, scale automatically and independently based on monitoring resources and traffic bursts, especially during events such as Black Friday. At the end, shipping services also communicate async with order service, and update order service with latest shipping status to update order status. Yeah, this is all I wanted to talk about this system. Any system similar to this system mm, is being handled almost the same. Let's say here it's an online shopping Amazon store. Maybe it is like reserving a hotel room or Airbnb. All these kind of services, which is online, and also it involves making an order, payments, and these are kind of similar, and all the concepts of transactional aspect of it, distributed transactions, concurrency, matters here. Concurrency, I didn't explain much about concurrency in this video, but in another video that I will have in another, course, I will explain more about concurrency and how to handle it. I hope you find this video and course useful. And as always, I'm happy to hear from you, your feedbacks. and let me know how you will go for this system design. Okay, thank you everyone. Have a great rest of the day and bye.